Have you ever wondered how engineers were able to measure irregular land areas long before computers and digital mapping? In this video, we're going to explore a fascinating mechanical instrument called the polar planimeter, a device that can measure the exact area of almost any shape simply by tracing its boundary. You'll see how I determined the area of a region on a country map using only mechanical motion, no digital tools involved. We need a polar Amsler planimeter, a calibration bar, and, of course, the area we want to measure. For example, the outline of a state or region on a map. The polar Amsler planimeter has an anchored pole arm fixed at a pivot point and a tracer arm that you move around the area you want to measure. If the pivot point of the anchored pole arm lies outside the measured area, we use this relationship for the unknown area S. You can see that this unknown area S is proportional to the number of revolutions N of a wheel at the bottom of the planimeter. If you want to know why this relationship holds, watch the end of this video. The reference area S0 is located on the back of the calibration bar. For this bar, the reference area S0 equals 100.2 centimeters squared. Before measuring the unknown number of revolutions, N, it is important to zero the planimeter and first measure N0. To measure N0, we firmly anchor the calibration bar at a fixed point on a wooden surface. We mark the initial position, for example by tracing this part, and then perform one full 360-degree rotation. This gives us one calibration revolution, N0. When tracing the boundary of the measured area with the tracer arm, we use the magnifying lens and align the center circle carefully along the contour. The tracing point follows the entire boundary until we return to the original starting point. That completes one revolution, N. The anchored pole arm with the weight remains fixed while the tracer arm traces the boundary of the measured area, in this example, the yellow region on the map. The number of revolutions can be measured with a precision of up to 1,000th of a turn. On the right scale, we begin at 0. This scale has 100 divisions. If we move across 20 divisions, we have completed 0.200 revolutions. This is 0.500 revolutions. This is 0.800 revolutions. This is 0.900 revolutions. And this is 0.950 revolutions. To determine thousandths of a revolution, we use the left vernier scale and observe which line aligns with a division on the right scale. If the second line on the left vernier scale aligns, the reading is 0.952 revolutions. If the fifth line on the left vernier scale aligns, the reading is 0.955 revolutions.
Here, it would be 0.956 revolutions.
And now let's show why this relationship we used is valid. This diagram and calculation help explain why the area S is proportional to the number of revolutions n. Here, S represents the measured area, and n represents the number of revolutions made by the wheel at the bottom of the planimeter while tracing the boundary of the area S. The L represents the length of the tracer arm of the planimeter. The wheel at the bottom of the planimeter lies at a distance L1 from the end of this tracer arm. As the measuring wheel rotates, it first travels a distance dh corresponding to an infinitesimal strip, and then an additional distance equal to L1 times d theta. So the total distance traveled by the wheel is dh plus L1 times d theta.
This infinitesimal area, ds, forms a trapezoid. When we rewrite the expression and integrate it to obtain the total area, we find that the result equals L multiplied by the total path W traveled by the measuring wheel minus a term that depends on the initial angle phi1 and final angle phi2.
Since we perform a full rotation from 0 to 360 degrees, the initial and final angle values, phi1, phi2, are the same. These terms therefore cancel out, and we are left with the result that the measured area S is proportional to the total path W traveled by the wheel. This path W is proportional to the number of revolutions. K is the constant of proportionality. However, we do not need to know this constant K because in the final formula we divide S by S0. The constant appears on both sides of the equation and cancels out. And that's how a polar planimeter measures area using pure mechanical motion. If this video helped you, give it a like and subscribe for more math and engineering content. Thanks for watching. See you in the next one.